more ridiculously small, like than this, right? This is like to scale. So here I have 2 clamps. That tiny little thing is the apodeme, and I managed to tie thread around the apodeme, grab onto the thread, and basically stretch it, right? And I just really wanted to put up there because really, like, I spent maybe a year and a half trying to figure out how to do this, to be able to tie knots around this thing and tie it. And just for a sense of scale, this is a millimeter, so ridiculously small. But yeah, I'm pretty proud of being able to. All right, so what did the results actually say? So here's an example from one animal. From one animal, I took the meris and the apodeme, and here you could see these red sections are where the spring constant was measured. So the apodeme here, it has a much lower slope, so it has a lower spring constant than the meris. And also, like, you can see that the area under this curve is much larger than the area under this curve. So, right, we were looking previously at the meris, asking whether or not that was a spring, and we were completely, like, just overlooking the fact that the spring could be somewhere else in the apodeme. And this is from one animal, so I did that for many other animals, and you can see that it's, like, significantly lower. The spring constant for the apodeme is significantly lower than that of the meris. So this statement, right, then becomes that apodemes store more energy than the meris and large spheres, which I thought was pretty cool. All right, so in a little bit of a summary, I looked at the mantis shrimp, the larger mantis shrimp, and I was really dealing with this level, what is the spring, or where is the spring? What structure stores the most amount of energy? And what I found in terms of just mantis shrimp are that large spheres store more energy in the apodeme than the meris, which is something that we hadn't realized previously, and it changes the way that we think about energy storage in the mantis shrimp, because energy storage doesn't necessarily have to be in one structure or the same structure across different species, which changes the way that we think about it. But I think even more in terms of, like, universally, what the final outcome of the study was that comparing spring constants of structures in series reveals where energy is stored. And this really, like, sets out an approach where we can move other studies up from this level to this level if they have this sort of connectivity. And I think that's really cool that we were able to put forth this new approach to be able to look at other systems. All right. So then now moving on to another system. And we're asking, how does the spring work in American bullfrogs? Quite specifically, are bullfrog tendons tuned to maximize energy storage? And so in terms of getting up this triangle, the goal is to get up here. How does the spring work mechanically? And touch a little bit on how does the spring work in its biological context. So if you've never seen a bullfrog jump, you probably have, but I just wanted to put this video up so we're all on the same page. If you just nudge it a little bit. They use their hind limbs to jump and escape. Sometimes they slip. But they're beautiful, just escape. And actually, bullfrogs have been known for their jumping ability so much that they've made competitions out of it. So this is from Calaveras County in California. I really want to go to one of these. But you'll see him drop his frog onto this platform and then go. And the goal is to get past this point and not to lose the frog, obviously. But so, like, bullfrogs are known for their ability to jump and escape. Right. So then we'll start off going up the triangle again. Start here, very foundational, very basic. Is there a spring in a bullfrog? And so what this study found was that if you look at the hind limbs, at the muscle itself, the muscle contracts for 50 milliseconds before the bullfrog starts moving, right? So think about this for a second. The muscle's contracting, the frog is not moving, right? So the muscle contraction has to be stretching something, right? So if you think about this in case of the muscle spring system and this white box being the animal doesn't move, the muscle contracts, therefore something has to stretch and store that energy. So in terms of answering this question, is there a spring in bullfrogs, it's shown that yeah, they do have springs. And we're moving up the triangle again, and now we ask, well, what is the spring in bullfrogs? Well, so this is the muscle that they measured here, and this is its connected tendon going all the way down. And this looks very, very similar to our muscle spring system, right? Where here you have the muscle and the tendon is acting as a spring. So in some cases, I just wanted to show that it's more obvious than multi-structured mantis shrimp that we saw what is actually the spring in bullfrogs, right? Then we move on to this part, and this is where I really wanted to get to, because I feel like this is like a large contribution that I've made towards the field. And we're looking specifically at how muscles and springs work together, right? In terms of answering their mechanics and their physics, how do they work together? What's their physical interaction between each other? And specifically, again, asking, are bullfrog tendons tuned to maximize energy storage? So in order to do this, I made a mathematical model. I'm going to step through it very slowly and make sure that I don't lose anyone. I'll try my best not to lose anyone. But it's actually not difficult at all. So we'll start with how do you connect a muscle and a spring. One way that you can connect them, again, is by the force, right? Their forces have to be equal, just like when you have two springs connected to each other, their forces have to be equal. So then what you can do is break down these forces down into their constituent models. So one simple one for the force of a spring is negative kx. So that is Hooke's law. It's the basic spring equation that you learn in high school and college physics. And just to go through it, k is your spring constant, so that's how stiff it is, right, in terms of the slope. And x of s is how much that spring is stretched. So to get more force out of your spring, you can either increase its stiffness, right? Intuitively, that makes sense. Like if you have a more stiff spring, you need more force to stretch it, or you could stretch it farther, right? And that's a very common thing in archery. Actually, the farther you stretch your bow, the more force it takes for you, the more force you have to generate to stretch it farther. So the force due to muscle is a little bit more complicated. Don't freak out. The thing that you really need to know is that the force due to the muscle of this is actually a modified Hill model. So it's based on physiological hypotheses of how muscles work, and it's divided up into three components. F due to activation, you can think about this as muscle effort, right? Am I putting in 0 effort, 100% effort, something in between? And the force of a muscle is also related to how fast it's contracting and also the distance that it contracts, right? So that's what those three things mean. So I'm gonna simplify this really quick right away and say that for right now, you don't need to know these things because they are dynamic factors, right? So a way to think about this is, you know that quotation, like, it doesn't matter where you get, it's how you get there. Or like, it's the journey, not the destination. This is the journey. And if we're only interested in maximum energy storage, we just care about the destination. How much force can the muscle contract? Can the muscle generate? So in terms of how to get there, we can ignore this for now. And this really is what we're interested in. One more simplification. You'll notice that there's two x's here. X of s is the spring stretch. Xm is how much the muscle contracts. And if you notice from our little model, whatever distance the muscle contracts, the spring stretches, right? So you see that the distance of the muscle that it contracts is the negative of the string stretch. So we can plug that in, simplify all this, and this is our final model. And that's actually it. That's our final model. So in case you're wondering what this actually looks like, because this probably like means nothing to no one, if you look at this graph, you see something like this, where here are the muscles at rest, here are the muscles contracted. So you can see at rest, you can generate your maximum force, and as you contract, you can generate less and less and less force, right? If you look at this equation here, K equals Xm, that's just a line, and this is your spring at rest, your spring that's stretched. So you see as your spring gets stretched, it takes more and more force, right? And because they're equal, we can set these, we can overlay these graphs together. And the really neat thing is this intersection point right here is the maximum stretch that the muscle can, it's the maximum stretch that the spring can have, and also the maximum that the muscle can contract. And if you look at the area under this curve right here, that's the maximum stored energy for that spring system, like total maximum energy that you can have by having a muscle that looks like this and a spring that looks like that, right? So what's really cool is that then we can address this question. Our bullfrogs are tuned to maximize energy storage by looking at empirical data of frog muscles and adding, connecting to it mathematically springs of arbitrary stiffness, where you have like an intermediate stiffness, right? A more stiff spring or a less stiff spring, right? And what you can do is you could ask, well, what stiffness of spring do I have to put in here to get the most amount of area under that curve, right? spring constant does that spring have to be in order to store the most amount of energy possible? And so